And let me go ahead and start recording. All right, so we want to get into Calc 3 material. So main topic for today's lecture is going to be coordinates, coordinate systems, and plotting in 3 dimensions. So Calc 3, it's really all the same stuff we've been doing. How Calc 3 is going to go, it's going to be the first half of the class is differential calculus, and the second half of the class is all integral calculus. And then, well, I guess the first third is uh, differential calculus. The second middle third is going to be integral calculus. And then the end, the last third of the class, is going to be tying it all together, is understanding all of the fundamental theorems of calculus, which describe how these differentials and the integrals interplay with each other. So it's really all of the concepts of Calc 1 and Calc 2, except now what we want to do is do it in 3-dimensional space. We live in a 3-dimensional world, or potentially higher, depending on what level of physics you're getting into. But for most of you guys who are engineers, computer scientists, if you want to model things like drones or automated driving systems, anything like that, you need 3-dimensional coordinates for moving objects through space, and we need a notion of how to do calculus on that. How are we going to model velocity and rates and times and derivatives? Well, we need our coordinate system. So that's what we're first going to build up to in this first chunk of the class. So let's go ahead and start off with notation. In Calc 1, you're working with what we call R. So I don't know how many of you guys have seen this notation. This R with an extra line through it, we call it Blackboard bold, is just going to be the set of all real numbers. When we say things like R2, this is the Cartesian plane. In set notation, we write it as the set of all x and y, such that x and y are both in R. So another math symbol that might come up is this guy here. This is, think of it like an E or some fancy script E. So it means element. So x and y are an element of R, or x and y belong to R. Essentially just saying that x and y are real numbers. And then R3 is our 3-dimensional space. So this is going to be our set of now x, y, and z, such that x, y, and z are in R. And just like you did when you first learned the Cartesian plane, well, we need to learn how to model our points in 3-dimensional space. So the coordinate system we draw follows what's called the right-hand rule. So in our typical XY plane, we have an x-axis and a y-axis. So if we have a 3-dimensional space, we need 3 different axes. So our axes are usually drawn with our x and y plane as our horizontal base plane and the z plane, or the z axes, as the vertical axes. So note that the x axis is coming out at us. Then the axes would continue up and down. And what we mean by the right-hand rule is this follows the right-hand rule, where if you use your index finger, your middle finger, and your thumb, this defines a coordinate system. So our index finger should always point in the first direction. So in our x-axis, this would point directly out at us. And then our y direction, this is hard to do on our camera here, our y direction is going to point to the right, following our middle finger, and then our z direction would point upward. So that is going to be the orientation of the coordinate system. The first coordinate should always point in the direction of your index finger, second coordinate in your middle finger, and then the third coordinate has to point in the direction of your thumb. So we could rotate this and twist it in any direction or any way we want to. You just would have to make sure that that orientation is correct. So how do we plot stuff? Let's pick a point, and let's say 1, -2, and let's say 3. So how do we plot a point? Well, we want to draw our tick marks. So tick marks are usually going to be drawn perpendicular to that given axis. So our X tick marks, let's draw this way. Our Y tick marks, we want to draw perpendicular to the Y axis, but they're going to be in the direction of the X axis. So our Y axis tick marks are going to look like this. And then our Z axis tick marks, we typically draw horizontally. And so how do we plot our points? Let's go ahead and extend our axes since we do have a negative number here. We want to go 1 on the X, so we walk out 1 on our X-axis, but then we need to go -2 on our Y-axis. So we need to walk from this tick mark on our X-axis. Let me go ahead and use a different color here. We are walking now in the Y direction, but we need to go perpendicular to the Y direction. And notice that our tick marks on our Y direction are parallel to our X direction. So if we wanted to extend our -2 on our Y, would be at this point here, we want to extend that out to our X line that we drew. But then we also need to go up 3. So this is going to be the tricky part. So from our Z, the other thing we could do, walk up 3 on our Z, we could walk out 1 on the X, and then go 2 on the Y. So it doesn't matter how we walk to this point, 1 minus 2 or 3, we could walk 1 on the X, -2 on the Y, and then up 3. Or we could go up 3, -1 on the X, -2 on the Y. And so that would create a little bit of a box here to find that point. And you can kind of see with these ghost lines that I've drawn that here at -2 on the Y, if I walked straight up, we'd be at another corner of that box. And actually that should be horizontal with that Z equals 3 line. So that would be our point here. So practice drawing more points and visualizing those. Of course, careful about your tick marks. Drawing is actually a useful skill, especially now in Calc 3. We'll test you guys drawing traces and curves. So I'll try to do my best job at making sure my drawings are nice for this lecture for sure. So now what we want to get into is now plotting curves and shapes. So of course, we usually have an independent and dependent variable for our functions. We haven't quite gotten into functions yet, but in our 2, our Y is typically our dependent variable. X is our independent variable. In Calc 3, our Z is going to be our dependent variable, and we're going to have 2 independent variables, X and Y. Regardless, what we want to be able to do is to graph shapes that are determined by equations relating these 3 variables. So to touch up on a bigger math concept, I want to talk about equations, which we want to think of as constraints, versus free parameters. Or free variables. So you ended with Calc 2. Some of the last concepts you talk about in Calc 2 are polar plots as well as parametric plots. And with parametric equations, you typically have one free variable or one free parameter, and then you can parameterize various curves. These notions are going to be used sort of intertwined in Calc 3, or we're going to be going back and forth between both of these types of concepts. And one way that you can think about this is equations are going to define what's called the codimension. versus the dimension of the mathematical objects, the mathematical shapes that we are going to describe. So for example, in parametric equations, you might have one free parameter. And what does that describe? It usually describes some curve in space. Whereas an equation, we want to think of as a constraint. And what do I mean by codimension? The codimension is going to be the dimension, or I guess we should say the total dimension minus the dimension of the object. Or I guess we should say, here, let me write it this way, that the total dimension minus the dimension is equal to our codimension. I'll explain that a little bit better here in a second when we see some examples. Sorry, give me one second. Okay. So what do I mean by this? Let's explore this concept and you'll get a better feel for it with examples. And let me know, so since I'm doing lectures on Zoom, let me know if I flip a page or if you guys are still writing. I can always bring back that page if I flip it too fast and you guys still haven't completed the notes. So examples. Let's say we want to plot an equation, x equals 3. So what do I mean by the total dimension? The total dimension of the space is going to be whether we are working in R versus R2 versus R3. It's the total number of variables that you want to consider in whatever equations you're defining. So when we want to plot this equation, x equals 3, we think of this equation as a constraint. So if we are in a one-dimensional space, and I have one equation, that is a constraint. So that means the mathematical object that is going to result from this equation is going to be one dimension lower than the total dimension we are working with. So one equation is a codimension one object. Well, it's a little weird in a one-dimensional space, because in a one-dimensional space with one constraint, that means the total dimension of the dimension of the object, we would subtract 1 from the total dimension, which means it's a zero-dimensional object. Well, what is a zero-dimensional object? A zero-dimensional object is just a point. So if we have 0, 1, 2, 3, that's going to be the object, and the plot in a one-dimensional space is now just a zero-dimensional object. It's going to be a point. Whereas in R2, well, now I have two variables. We've got x and y. And so we are in R2 with one constraint. Again, a codimensional one object means the dimension of the object is going to be 1. And so we will get a line at x equals 3. And then if we want to do this in R3, so let's try to draw a reasonable graph. I'm going to bring the y-axis out like this. So again, with our axes for R3, follows the right-hand rule, however you want to draw your x, your y, and your z. So index finger, middle finger, thumb. And we have x equals 3. So you always want to draw your tick marks for x parallel to the y. So x equals 3, we know we're going to pass through this point, but y and z can be anything. So what we're going to have in R3 is going to be this plane. So maybe we can use some color here. So it's this plane that is sitting out at us at x equals 3. Sorry, I should have drawn, let's draw this a little better, parallel to that y-axis. There you can kind of see it a little bit better. So I guess to rewrite that last statement, our dimension plus codimension is equal to our total dimension, or the total spatial dimension you're working with. So let's take a look at this again. So the dimension of the object here is a 0-dimensional object, which means it's codimension 1. All of these are going to be codimension 1 because that's going to be the number of equations. And then this is our dimension of the object. We can think of the free variables involved. So here we have no free variables. We just have that one point. Over here, well, we've got one free variable, namely our x is constrained, but y can be anything. We can choose y whatever we want. So we have one free variable, one equation, and that gives us our total dimension in R2. In R3, what was our constraint? Our equation again, x equals 3. That gives us our codimension. The number of free variables we have, well, how did we graph this plane? Well, we said that x had to be 3, but our y and z variable, as long as I start at this point on 3 on the x-axis, I can walk parallel to the y-axis and parallel to the z-axis however much we want. In other words, our y variable and our z variable are freely chosen. I can choose any other y and z value as long as that x value is 3. And the set of all of those points gives us this plane. And that plane is a 2-dimensional object, our two free variables being y and z. So just for the sake of future, the end of this lecture, let me check time. We've got about 20 minutes. So basic planes, you want to know how to graph. Planes, you can talk about them as traces. I'll expand upon what do I mean by a trace. It's essentially setting one of the variables equal to a constant. And we already saw something like x equals 3. So a common graphing technique, which we'll get into, is picking a constant value for one of the variables. Essentially what this amounts to is taking a plane and then slicing your object and seeing what kind of curve results. So for example, z equals 1, we would walk up 1 on z, and then our free variables x and y can be anything. So we would have a horizontal plane through the point z equals 1. Y equals minus 1. And let me go ahead and actually label the axes. So let's go ahead and extend our negative axes. And y equals minus 1. We're going to be over here. So here we're going to have a plane once again, and that plane is going to be extended forward and backwards, and then up and down. Through that point, y equals minus 1. Everyone good? Okay, so let's kind of build upon these graphing skills a little bit, and let's talk about cylinders. So common objects that we are going to find are called cylinders, and cylinders is going to be a broad term for types of graphs. Everyone kind of understands what a cylinder is if you just take a piece of paper and roll it up. We broaden that definition a little bit. And let's go ahead and just start with an example. So let's graph the equation y equals x squared in both R2 and in R3. R2 is pretty simple. We've got our standard parabola. In R2. And now how are we going to graph this in R3? Well, let's think about some of the concepts we were just talking about. And just as a heads up, this concept of dimensionality and codimensionality, not in the book, not in the lecture notes, but I do think it's a good way to organize things in your brain, especially as you start to work with these types of objects. And if we did, or if you guys are interested, we can talk about parametric surfaces later this semester, especially since you guys are the honors class here. So how do we graph y equals x squared? Well, it's a codimension 1 object. Since it's one equation, codimension 1, which means the dimension of the object in R3 is going to be a 2-dimensional object. This is pretty standard. So anytime we have one equation or one defining equation in R3, the surface or the object that's going to result is a 2-dimensional object, which we call a surface. And so how do we graph this surface? Let's go ahead and draw our axes. And I'm going to go ahead and keep the y-axis horizontal here, left and right. And our x-axis here. Well, codimension 1, it's a 2-dimensional surface. What variables are free? We have to think about. We should have 2 free variables. Well, just like in R2, we have x and y, we have an independent and a dependent variable. Here, our y is our dependent variable. It's not a free variable. I can choose x freely. I have one free variable in R2, and that's going to be our x. We choose x freely. Y is going to depend on that value of x. Over here in R3, well, it's the same equation. So we can think of y as our dependent variable, and x is going to be our independent variable. So again, let's go ahead and draw our tick marks. This is going to be harder to draw in 3-dimensional space. But again, especially in engineering, always important to know how to draw, especially if you get into CAD systems and you guys are aerospace or mechanical, you're going to get into stuff like that. And so having an understanding of how to visualize and draw things by hand is going to be very important before you have a computer do it, and vice versa. Having a computer do it and making sure you can check your own mentality of, is my computer doing something right? Did I code this right? How can I check myself as to whether we did it right? So let's go ahead and draw our points. And again, we want to draw, so 1, 1 and -1, 1. So we're moving parallel to those tick marks, parallel to the axes. And then we've got the 0.24. So let's go ahead and try to draw those. -2, 4 as well. So we've got our parabola now sitting on this XY plane with our perspective as shown. And our x was a free variable still. Our y is our dependent variable. Well, where is z? Z is not listed in the equation. What does that mean? That just means z can be anything. What does that mean? That means we take our drawing in the XY plane and just extrude it in that direction. So This is why we call it a cylinder. It's essentially just taking whatever base shape you have that's defined by that equation and then extending it in the other direction. So this whole shape is going to look like these parabolas that are now extruded up and down. In general, so a cylinder in R3 is an equation missing a variable. Or one of the variables doesn't appear. So how do you graph it? Graphing the plane with the two variables given. And then you just extend it in the direction of the missing variable. So try some examples on your own. Take that same equation, just permute the variables around. So try to graph z equals x squared or z equals y squared. So try those on your own. Not going to be too difficult. Z equals y squared in particular. Well, here's our y equals x squared. If we just take z as our dependent variable and y as our independent variable, in the zy plane, you can graph the parabola and then you would extrude it forward and backward along the x-axis. And that reminds me, there is one thing I guess we didn't quite go over with the axis planes. So to go back for 1 second, all of the axes, hopefully everyone understands, our x-axis is the x-axis, the y-axis is the axis with the y label, z-axis is the z-axis. Going back to our planes and traces, if we consider, say, the plane z equals 0, well, that's just the plane defined by where our z coordinate is 0. This is going to be what we call our xy plane, or our standard plane created by the x and y axes. Likewise, if we had x equals 0, well, now our x coordinate has to be 0. We are flat on the front and back face, so that's going to be our yz plane. And then likewise, our y equals 0 plane. So if our y is 0, I can go forward and backwards and up and down. That's going to be our xz plane. So just some common terminology we'll be using throughout the semester. Does that make sense to everyone? And then, of course, if we had changed those numbers, our plane z equals 1 is going to be parallel to the xy plane. So it's going to be a horizontal plane, then moved up 1. Our plane y equals -1. It is parallel to this xz plane. We just shift that whole plane left 1. Okay. So some other things we want to get through today. Might have to skip some of these examples. We only got about 10 minutes left here. Or no, are we about finished? Our class is over at 3:20, right? Yeah, so 3:20. Looks like we only got 1 minute left. Let's go ahead and finish up with the distance formula. And then maybe we can talk about traces on Wednesday. So distance formula. In R2, we usually have 2 points, x1, y1, and x2, y2. What is our distance formula? It's the Pythagorean theorem. We take our change in x, we take the change in y, we square both of those and add them together. In R3, well, now we have, oh, sorry, here. We'll have x1, y1, and z1. So we've got some point x1, y1, z1. We'll have another point x2, y2, and z2. Our distance is very similar. We take the change in x squared plus the change in y squared plus the change in z squared. Okay, so we are out of time for today. I would say look over the notes. So look at Oskimo's notes and the notes after this distance formula part. We get into a little bit more formulas, and we'll cover this again. So this is bleeding into topics from chapter 10.6 or from section 10.6. And you want to practice sketching things like x squared plus y squared equals 4, and actually with an equation z equals minus 3. This is a good one to think about because now I have 2 equations. So 2 equations means we are codimension 2, which means the object we're going to be drawing is just a one-dimensional object. It's actually just going to be a curve. So everyone can hopefully recognize that this is a circle. So it's going to be a circle that's only going to be stuck in the plane z equals minus 3. So it's going to look like a circle moved down minus 3. Or I guess I should say a circle or a sphere starting at x at, or no, sorry, it'll be a circle moved down minus 3. And then there's other examples of just planes. And then equations like y squared plus z squared equals 4. And again, our typical methods for drawing these, you often want to take a variable and set it equal to a constant. And then look at that trace. We'll talk a little bit about that on Wednesday.